Okay, good afternoon everyone. Today I am going to discuss about the computer network subject, Unit 4. So, in the previous videos we have discussed about the TCP connection release. So, I am going to continue the next topic. So, before going to explain that, just I am recollecting the points again. So, in this we have discussed about the Internet Transport Protocol UDP and introduction to UDP, and this is the UDP header diagram. In this we are having source port and destination port with UDP length and checksum. So, it is a 8-byte header, and maximum length is 65,515 bytes, and checksum also provided for extra reliability. It checksums the header and the data. Okay. So, next we are we have discussed in the previous video, that is remote procedure call. So, whatever the message we are transmitting from one node to the another node, it is not visible. So, then we can say it is a remote procedure call. And next coming to, this is the diagram of the remote procedure call. In this diagram I am having the client CPU and server CPU. In client CPU, in the first step, client CPU will be called to the client stub, and here the message will be parameterized, and it can be sent through the operating system, and it will be received at the receiver server side, and through the operating system it went at the server stub, and server stub it will be at the server CPU, it will be reversely operation will be occurred, like client CPU will be happen. So, this is the diagram of the remote procedure call, and these are the steps which I have discussed in the previous class. And next coming to real time transport protocol, and this is the diagram of the RTP real time transport protocol. And transmission control protocol, we have discussed about TCP service model, TCP protocol, TCP segment header, TCP connection establishment, TCP connection release. These are things we have discussed in the last class only. So, this is the introduction of TCP and TCP service model, and these are the tables. This is the TCP protocol and TCP segment header, and next this is the diagram, and this is the these are the explanations of this diagram. And next this is the TCP connection establishment, and next we have TCP connection release. Up to here we have discussed in the previous video. Now I am going to continue this TCP sliding window. So, what is mean by TCP sliding window? So, TCP decouples the issues of acknowledgements of the correct receipt of segments and receiver buffer allocation. For example, suppose the receiver has 4096 byte buffer as shown in the diagram. So, this is the diagram I am having. So, this is the diagram. Here application does a 2K write, sender and receiver. So, I am sending the 2K with sequence 0 to the receiver side. Okay, at first I have doesn't have anything, 0 to 4K, this one, this is empty. When I am sending the 2K with the sequence number 0, at the sender whatever the buffer receiver buffer having, it will be filled with 2K. It is a 4K size, 2K is filled and 2 is empty. Okay. Again I am sending the after receiving the message from the sender, it send the acknowledgement 2048 and win with 2048. Okay, he is sending the acknowledgement. Application does a 2K right. Again I am sending the 2K. So, sequence number is 2048. So, okay, and our full buffer receiver buffer is full with 4K. Okay, again I am sending the acknowledgement, win is 0. Okay, and acknowledgement is 4096. Okay, so this is the acknowledgement. Sender is blocked here. So, again application reach 2K. Okay, application reach 2K. So, then acknowledgement in 4069 win 2048. Okay, sender may send up to the 2K. This like the communication will be occur. So, if you see the explanation, we can understand easily. So, if the sender transmits a 2048 byte segment that is correctly received, the receiver will acknowledges the segment since it has only now has only 2048 bytes of buffer space. Until the application removes some data from the buffer, it will advertise a window of 2048 starting at the next byte expected. So, now the sender transmits another 2048 byte. So which are acknowledges but not advertised window is of size 0. The sender must stop until the application process on the receiving host has removed some data from the buffer, at which time TCP can advertise a larger window and more data can be sent. So okay, more data can be sent. This is the explanation of this diagram. Next, TCP conjunction control. So what is mean by TCP conjunction control? So when a load offered to any network, when node offered to any network is more than it can handle, conjunction builds up. The internet is no exception. The network layer detects conjunction when queue grow large at routers and tries to manage it, if only by dropping the packets. If it is to transport layer to receive conjunction feedback from the network layer and slow down the rate of traffic that it is sending into the network. In the internet, the TCP plays a main role in controlling conjunction as well as main role in reliable transport. Okay. In this is called conjunction control. Okay. So in this conjunction control, we having the transport protocol uses additive increase, multiplicative decrease. Additive increase, multiplicative decrease control law is response to conjunction signals from the network would coverage to a fair and efficient bandwidth allocation. TCP conjunction control is based on the implementing this approach using a window and with packet loss as the signal. So to do so, TCP maintains a conjunction window whose size is the number of bytes the sender may have in the network at any time. The corresponding rate is the window size divided by the round trip time of the connection. TCP adjusts the size of window according to the additive increasing, multiplicative decreases. Okay. So it follows the rules of AIMD. Okay. So next, coming to TCP connection management modules. So in this we are having the TCP conjunction management modeling. So to stop the required establishment and release the connection can be represented in a finite set machines with the 11 states listed. So in each state certain events are legal. With legal event happens, some actions may be taken. In some other that events happens, an error is reported. So that events are closed, listen, synchronous received, synchronous sent, established, find, wait 1, wait 2, timed wait, closing, close wait, lost acknowledgement. These are the different states of events occurred in this connection management modeling. Okay. So TCP in this we are having some points of use, like the server does listen to settle down the synchronous comes in the server acknowledges, it does not synchronize received state. Okay. And the server is the signaled when it too does a close and find is sent to the client. So these are the different points of view we have discussed in the TCP connection management. Okay. Next, coming to performance problems in the computer network. So what is mean by performance problems in the computer network? Okay. So in this having the conjunction. So in the computer we are measuring the performance problems. Okay. First one is conjunction. If more traffic suddenly arrives at the router than the router can handle, conjunction will build up and performance will suffer. It means what? Whenever the two devices in communication, middle of the two devices we are maintaining some routers in order to handle the problems like conjunction control. Okay. So that routers will be handle all the whatever the traffic arrive at the routers, and okay, the conjunction will be built up and the performance will suffer. Okay. So when congestion is built up, and then performance will be suffered. It is not caused by temporary resource overloads. Okay, this is called the congestion. Next, the second one is structural resource imbalance. For example, I have if a gigabit communication line is attached to a low end PC. Okay, gigabit communication line is I am going to attach to the low end PC, okay, personal computer. The poor host will not be able to process the incoming packets fast enough, and some will be lost. So whenever I am attaching the gigabit communication line to our personal computer, so the host will be poor, will not be able to process the incoming packets fast and some data will be lost due to that. So these packets will eventually be retransmitted. So whatever the data lost, the transmission will be again retransmitted, adding delay, wasting bandwidth, and generally reducing the performance. Whenever the performance level is poor, our traffic bandwidth and generally performance levels will be reduces. So okay, so this is called structural resource imbalance. Okay, so next, synchronously triggered overheads. Synchronously triggered overhead. If a segment contains a bad parameter, so when a segment contains a bad parameter, that is the port for which it is destinated, if many cases the receiver will be thoughtfully send back an error notification. Okay, so whenever our poor communication will be occurred, so the receiver will be send back a error notification. If any error is occurred at the receiver side, or any data will be lost, if data will not lost, it will send the negative acknowledgement. So this is something, negative acknowledgement will be or error notification, some notification will be received at the receiver. Okay, so now consider what would happen if a bad segment is broadcast to 1000 machines. Each one might send back an error message. So if suppose I'm using 1000 machines, so having the 1000 whenever I am maintaining the 1000 machines, so each and every machine has a bad segment. So every system will be get the send back the error message. So the resulting broadcast stream used cripple the network. Okay, so that is called the synchronously triggered overloads. Next, lack of system turning. So if a machine has plenty of CPU power and memory, but not enough of the memory has been allocated for buffer space, flow control will slow down segment reception and limit the performance. Okay, so lack of system turning. Okay, next, coming to performance problems in computer networks. So what is the performance problems in computer networks? So this is the diagram which has seen here. So in this I am having the performance level. So data I am transmitting from one node to the another node. At the diagram A, I doesn't send anything, t is equal to 0. Okay, at t is equal to 0. At B, I am sending 500 microsecond with the time. By maintaining the time, I am sending some data packets to the source to the destination. Okay, so after 20 milliseconds, after 20 milliseconds at the C diagram, after 20 milliseconds the data is reached at the receiver side. Okay, after receiving the receiver the data, after 40 milliseconds it sends the acknowledgement to the sender. So this is the transmission state of the megabits. Okay, state of transmission 1 megabyte for San Diego to Boston. Okay, so this is the performance problems in the computer networks. So next, coming to network performance measurement. So what is mean by network performance measurement? We having some steps of performance improvement. So that is measure relevant network parameters performance, try to understand what is going on, change one parameter. So now I am going to explain this. So while measuring the network performance, we have to take care about the following of this. So whenever I am maintaining, if I want to maintain the network performance, I have to follow these steps. Make sure that sample size is large enough. So do not measure the time to send one segment but repeat the measurement say 1 million times and take the average. Having a large sample will reduces the uncertainty in the measured mean and standard deviation. This uncertainty can be computed using standard statistical formulas. So, this is called the first condition we have to follow when we are measuring the network performance. Second one is make sure that the samples are representation. So, ideally the whole sequence of 1 million measurements should be repeated at different times of day and a week to see the effect of different networks conditions on measured quality. For example, there is a heavy conjunction at 11 a.m. and 1 p.m. but no conjunctions at noon. Okay. So, this is the another rule we have to follow. Third one is catching can wreak hack with measurements. Repeating the measurements many times will return an unexpectedly fast answer if the protocols use catching mechanism. So, repeating measurements many times will be returned unexpectedly, but it can be done very fast due to the catching mechanism. For instance, fetching a web page may involve a network exchange the first time and then return the answer from a local cache without sending any packets over the network. So, the result from such a measurement are essentially worthless. So, unless you want to measure cache performance. So, this is the third rule we have to follow whenever we are measuring the network performance. Fourth one is be sure that nothing unexpected is going on during your test. Making measurements at the same time that some user has decided to run a video conference over your network will often give different results than if there is no video conference. So, this is the fourth rule you have to follow. Next one, be careful when using a coarse grain clock. So, computer clocks functions by incrementing some counter at regular intervals. For example, a millisecond timer adds 1 to a counter every 1 millisecond. Using such a timer to measure an event that takes less than 1 millisecond if possible, but requires some care. Some computers have more accurate clocks, but there are always shorter events to measure too. So, note that clocks are not always as accurate as precious with which the time is written when they are read. So, this is the fifth rule, and sixth rule is be careful about exploiting the results, extrapolating the result. Suppose that you are make measurements with simulated network loads running from 0 ideal to 0.4, 40% of capacity. For example, the response time to send a voice over IP internet protocol packet over a network, it takes much care while using some simulated network loads and statistical methods to extrapolate the results. So, these are the different measurements we are following when measuring the level of the network. Okay. So, up to here we have completed the unit 4. Okay. Thank you.